Hi guys, welcome back to what hopefully is going to be our final video on matrices. Woo! Now this video is going to be just a little longer than the others in order that I can successfully finish all the key features I wanted to touch on, as well as we are not going to perform fully with questions in this video. I'll just refer you guys back to the relevant videos that you would need to look at to see the solutions for certain aspects of questions. So first of all, when you're solving matrices, right, you will encounter a series of situations which takes place because these matrices essentially deal with a lot of equations. For example, I'm going to look at a basic simultaneous equation here. X minus y equals 1, and equation 2x plus 2y is equal to 4. So we have a pair of simultaneous equations, and you guys know we can write these in the matrix form where we take the coefficients of the variables and we simply rewrite those in a matrix format. And we can do several things with these matrices. You can find the inverse of this matrix. You can hence solve for values of x and y. If you want to remember or recall how to find the inverse of a matrix, please see previous videos on finding the inverse of a 2 by 2 matrix. As well as if you did not want to use the method of finding inverse in that form, you can augment these matrices as well, and you can reduce to the identity matrix form, where you could have also written your matrix in this form, -1, 2, and augmented it with the identity matrix. And of course, after a series of row reductions with the intent to get your identity matrix on the opposite side, whatever values are left would end up being the inverse if this matrix were called A. All right, guys, so please see my previous videos on finding the inverse of a matrix. Now, essentially what I want to focus on today are the types of solutions you are going to encounter and what they mean during the processes of row reduction to echelon form or finding the inverse of a matrix. All right, for example, in this question, if you were to use inverse method and eventually you got values for x and y, say you were able to successfully get values of x and y such that you got something like this, then this means that you had a clearly situation where you had your lines. Remember, this is a linear equation. This is also a linear equation, so they both represent straight lines. So these two straight lines would said to be intersecting at this point here, 2, 1. And if you are able to achieve a situation where you find using a matrix method, you get a nice, clean, clear, unique solution, then these two straight lines would said to be intersecting. Would say to be intersecting, sorry. Also, if you had a situation where, so let me just draw a line here, guys. All right, so that's one case scenario that can happen, and these lines are said to be intersecting. Let me show you guys a second case scenario that can happen. Say, for example, you had a system of equations, x plus 2y is equal to 3, and 2x plus 4y is equal to 4. Once again, both these lines are two linear lines or two straight lines that are on a graph. And let's just say we applied the row reduction method to echelon form, and we ended up getting a situation where we had 1, 2, 0, 0, and 3, -2. Now remember, for this to be essentially in the identity matrix format, if you were trying to find the inverse, you would have wanted to get the 1, 0, 0, 1 form on your left. Now, if you are not able to achieve this and you achieve a situation where you have zeros on one side and you have a value on the other, then this situation takes us into a case scenario where really what you are getting is if you were to rewrite this using your x and y values, what you really have is that x by y gives us values of 3 and 4, and multiplying that out, what this solution is telling us is that x plus 2y gives us 3, as well as 0x plus 0y is giving us 4. So that second sort of solutions, 0 being equal to 4, is just, that is incorrect. That is definitely not a solution. So in a case like this, what we'll say is that there are actually no solutions for the values of x and y. And whenever we are trying to find solutions for a system of two linear lines and we can't seem to find any, it means that these lines are parallel, or there is no intersection between them. Okay, so parallel lines. All right, that's why you're not achieving a solution on a graph. There is no intersection taking place for a value of x and y to happen. All right, let me show you guys a next case scenario that can also happen. All right, so I'm gonna draw my line here. Let's say you have another system of equations where you have clearly two straight lines. You know that because they are linear. I'm sorry, this is supposed to be x. Plus 4y is equal to 8. So once again, you have two linear straight lines. So you're wondering, are these lines intersecting? Are these lines parallel to each other? So there are no solutions. What's happening with these lines? Well, let's just say you performed a row reduction or whatever you needed to do to find the inverse of this 2 by 2 matrix. And you ended up getting a situation where in reducing, you get this. You get something like this. All right. Well, this is definitely going to happen for this question. These are the actual solutions for this question. So say you get this, and then you go ahead and you take your time and you expand. So that's 3 multiplied by x gives us 3x plus 2y being equal to 4, as well as you'll get 0x plus 0y is equal to 0. So on the top, 3x plus 2y being equal to 4, that holds. That seems fine. And on the bottom, you have 0 is equal to 0, which also holds. That's fair. That's definitively correct. That's not mathematically incorrect. So therefore, what's happening here in this case is that we have a situation where you have two lines that seem to coincide, or they actually lie one on top of the other, right? Where there's an infinite set of solutions because the lines are coinciding. And how is there an infinite set of solutions? Well, if you were to consider the only equation that's actually giving us any sort of values, all right? So after your row reduction, say you got 3x plus 2y to be equal to 4. And obviously, you can't solve for x here, you can't solve for y, but you can make one of them a subject of the formula in terms of the other. let's just say we choose to make x the subject of the formula, then that gives us 4 subtract 3x all over 2. Sorry, 4 subtract 2y all over 3. Then in a case like this, if y were to take any value, any constant value, let y be any value such as k, then what's happening here, or what we see happening, is that if y is any constant value k, then no matter what values y happens to be as a constant, be it 3 or 4 or -5, the values of x will also belong to the system of real numbers. So you will also get values of x coinciding with the relative values of y. So it seems that the solutions for a situation like this is unending. So what you want to look for is a case where whenever you are applying row reduction and your entire row reduces, or one entire row reduces to all zeros, then you can safely say that there's an infinite possible situation of solutions for this system of equations. Going back to the previous example, if your row reduces to all zeros before your augmented sign, then there's no solutions if on the opposite sign there's also a value, because that doesn't make sense. You can't have zeros on one side and then -2. 0 cannot be equal to a value of -2, or vice versa. So no solutions if you have a partial situation where one side of your augment reduces to zeros and not the other. And of course, with all clarity, if you are definitively performing a row reduction and you get nice, clean, clear, crisp solutions, then it must mean that your system of lines or linear equations are definitively intersecting with each other. So that's a recap there, what to look out for. One last time on screen, I will highlight the last two. All right, so if something reduces to the nature where you have 0, 0, -2, this is 1, 2, 3, say this situation here is not possible, so there are no solutions. And if you have a situation where you get your entire row being reduced to zeros, then you have a system where you have infinite solutions. All right, so those are some nice points to note when you are dealing with a system of linear equations. Okay, guys, so I just want to talk about by extension when you are dealing with 3x3 matrices now. So let me just give you guys, if you want, a heading. If you have a system of linear equations as well, so you have all straight lines, linear equations, but more for the 3x3 matrices or the 3x3 three unknown situation where you have x, y, and z. Then how do you know? Well, it's the same process that's going to apply. The first one, you will have a unique solution. Obviously, if you are able to achieve a system whereby you end up getting a situation that looks like this. You have reduced to your echelon form and you get values as such. Let's just say you had -5, 2, 0, 0, 0, 1, 2, 1. All right, notice that in these three rows, you have a situation where none of the rows have fully reduced to zeros, nor do you encounter a situation where both sides are reducing to zeros or only one side. So when you see that you have that taking place, you have unique solutions. The second case scenario that can happen is where, say for example, your row reduces to a situation where you're going to get no solutions. And this will take place if you have something like 1, 2, 3, and you get a value there. Then you get 0, 4, 0, 0. And then finally, right. So there are always no solutions when you encounter the case where one side of your augmented matrix is all zeros and the other side has a value. Remember, 0 can never be equal to 9. That's just not correct. So therefore, there will be no solutions in a situation like this. And then finally, the last case scenario where you are going to have a situation where you're going to get infinite solutions, right? Infinite solutions will look like this. You will get a case where you have 1, 1, 2, 4, 0, 5, 7, 0, and then you'll get all zeros as well as 0 on the other side. So when you encounter a situation where both your left and right hand side of your augmentation are all zeros, then it's said to have an infinite system or set of solutions. And essentially, those are the three cases you also look for in your 2 by 2 matrices. So it's intersecting. It's definitely intersecting if you are dealing with a 2 by 2 system of equations, and it will be coinciding, or there will be 2 parallel lines. Okay, guys, so in a nutshell, that's it. That's as much as you need to understand in terms of what your solutions may turn out to be and what you can glean from what you get in your augmented forms of matrices, right? So if you want to see more examples of these, I can do a few more in a tutorial. However, I would say that understanding unique no solution and infinite solutions has everything to do with a concept more so than doing with examples. But nonetheless, if you guys would like to see like fully with examples and so on as to where a situation is, you're going to get like an intersection of 2 straight lines or so on, I can do questions. Just hit me up with a comment down below and I'll be glad to create a tutorial for you guys. So guys, that brings us to the end of matrices. Take note that matrices can be applied to solve a lot of stuff. Matrices are used in chemistry when they're mixing and creating chemicals with percentages and the solutions. They're used in electricity, creating circuits and so on. They're used in the industry, in the manufacturing industry. They're used in pretty much everywhere you think about it. Matrices can be used to find solutions and values, especially when it involves a series of a lot of unknowns. So if you think that it's not applicable to your daily life, just do some research, guys, and I can even probably bring in a video if you wanted to see the impact of matrices on your life every day. It's for those of you guys who like to do graphic designs and pixeling and you know, rendering and so on. It's very popular. It has its place. Okay, it definitely has its place. But anyway, guys, that's the end of matrices in the raw form as it can be. I hope you guys enjoyed those videos. Remember, I always keep it real. I try my best to make these classrooms seem like if you're sitting in school live, and I hope you guys are enjoying them, and I look forward to seeing you when I begin my new topic of we're going to be doing with some dealing with some differential equations. Hopefully next time you guys see me on here. So I'm looking forward to working with that because I love differential equations way more than matrices. So yes, differentiation is my thing. Okay, guys, so not trying to keep this video long. I hope you guys are doing well. And remember, always keep learning, always keep trying. And I wish you all the best. Take care and goodbye.